Hello and welcome to today's lesson. Today we're diving into the exciting world of physics, specifically the concept of speed, velocity, and acceleration, so fundamentals of motion and kinematics. Whether you're gearing up for your A-level exams, GCSE, or just eager to expand your knowledge, you're in the right place to recap some fundamentals. Let's start with the basics. So what exactly is speed? Well, in simple terms, speed is how fast an object is moving, so how much distance it is covering in a particular time. And if you remember it like that, it's how much, or better yet, internalize, it's how much distance you're covering in a particular amount of time. You're internalizing, that definition both as something you communicate in words and also in mathematics. Yeah, if you can be attaching the equations and the terminology to, appreciate that those are the same things, but just in different languages, for basic concepts like this, it'll become really, really useful, powerful tool when you come to more complex things along the line, right? So it's a measure of how quickly something moves from one point to another. Imagine you're riding a bike, or imagine you're in this car here, right? If you cover a distance in a short amount of time, you're going at a high speed. But if it takes you longer to cover that same distance, your speed is slower. And you can, stick some simple numbers into that equation up there, and boom, you've got that kind of all organized in your head. Now let's talk about velocity. Velocity is very similar to speed. It is the vector pair, the vector counterpart to speed in the scale vector pair that they are. Okay, so we'll try and explain what that means by pointing out the one crucial difference velocity has with speed. It includes direction. In other words, velocity not only tells us how fast something is moving, but also what direction it's moving. Okay, so for example, if you're traveling north at 60 kilometers per hour, your speed is 60 kilometers per hour, but your velocity is 60 kilometers per hour north, right? That is the difference between a scalar quantity and a vector quantity. Both contain magnitudes, right? Both are telling us 60 kilometers per hour. But the vector contains a direction as well. So scalars, just magnitude in the quantity. Vectors include a direction as well as the magnitude. So we've got two more examples here. We've got the car. Both of them have the same scalar value of 25, right? They're both traveling at a speed of 25 meters per second. However, they are traveling in opposite directions, right? So that's signified in the vector quantity by this positive and this negative. The positive and the negative are showing that they are traveling in different directions. So although they have identical speeds, because the magnitude are the same, their velocities are different because they are both moving in different directions. So that's the key difference between speed and velocity. So if you want to calculate velocity, then we can just be thinking velocity equals displacement over time. Displacement being the vector pair to distance. Okay? So here we go. Here we've got what we were just talking about exactly before. I've got speed, simply just the magnitude, and then I've got my velocity, right? Speed is the magnitude of the velocity. Velocity needs to also include the direction. That's an imperative when talking about vector quantities to signify the direction, either written or with pluses and minuses to or angles to show what direction something is traveling at, angles or bearings. So here we go. Once again, we've got a nice little graphic here that's telling us what we've been talking about. Speed is defined as the rate of change of distance. It is a scalar quantity, just magnitude, and its unit, if we're talking about it in terms of SI units, is meters per second. And there I've got my formula of speed equals distance over time. On the other side there, I've got velocity. Velocity is defined as the rate of change of displacement, right? And speed, sorry, got to mess that up there. Displacement and distance being scalar vector pairs, much like speed and velocity are, all right? Velocity is the first time derivative of displacement, all right? So I've got the concept of displacement represented by S here in our kind of SUVAT symbol terminology, divided by time, giving me velocity. And since that displacement has a direction, the direction continues into the velocity. And the unit is still meters per second because they have the same magnitude, right? They have the same magnitude. They are both, a derivative of a distance, a time derivative of a displacement. The velocity, of course, includes the direction as a vector as well. Lastly, let's tackle acceleration. Acceleration is all about changes in velocity. When an object speeds up, slows down, or changes direction, it's experiencing acceleration. Okay, so I've got my first example here of I've got this guy running and his velocity increases. The magnitude of his speed increases. He is speeding up. All right, so maybe he was going at, I don't know, he was 6 minutes per kilometer, and then he's gone to 5 minutes per kilometer. He's sped up, he's accelerating. On the other hand here, we've got something near and dear in my heart. We've got some skateboarding. We've got this individual, the effects of friction are causing them to slow down. Yeah, their velocity is decreasing. The magnitude of the speed is decreasing, so they're slowing down. Then I've got this B here. I've got this B, which is constantly changing direction. So as it's changing direction, that means it's accelerating, because accelerating is a change in speed, change in the magnitude of the velocity, or a change in direction. Yeah? So you put that together, it's a change in velocity, because velocity was defined by magnitude, like our first two examples, or direction, like our last example. A fan that's spinning around is a really good example of acceleration. All right. So if I got a fan spinning around, I've set that to whatever, setting and speed it's going at, and I've got it spinning around. That's accelerating, because although the magnitude of the velocity, the speed, might be the same at every single point, yeah, it's constantly changing direction. And if something's changing direction, that means its velocity is changing. And if something's velocity is changing, that means it's accelerating. So that fan spinning around at a constant speed is in fact accelerating. Let's have a little look at the equation here. So now we've got the next time derivative of displacement. All right, we had displacement once, we had a time derivative, and we got to velocity. Now we're going to get to the next time derivative, and we're going to get to acceleration. All right, change in velocity over change in time. That's going to give us the average acceleration of a body in motion. Getting a little bit into the units here again. First, we got it in words, right? The unit of acceleration is going to be equal to the unit of velocity divided by the unit of time. We established that the unit of velocity is meters per second. It's pretty clear the unit of time is seconds if we're following the SI system. So my unit of acceleration is meters per second squared. Now, for me, I think it's kind of like, it's very, I assume for you as well, it's quite easy for me to conceptualize the idea of a meter. And it's quite easy for me to conceptualize the idea of going through a meter every second, meters per second. Cool. It's very difficult for me to conceptualize the concept of a second squared. And then so it's even more alien for me to conceptualize the idea of going through a meter per every second multiplied by itself, second squared. So I think for conceptual understanding, saying meters per second squared doesn't really help me. What does help me, though, is this which I have here. I can think about a meter per second, and I can think about going a meter per second. So I typically like to, when I'm saying out loud or narrating in my head, I like to think of acceleration as meters per second per second. Okay? So if I had an acceleration of 5 meters per second, that means every second I am traveling an additional 5 meters per second. So in second 0, let's say I'm traveling 0. I'm accelerating by 5 meters per second. 1 second later, I'm now traveling 5 meters per second. I'm still accelerating at 5 meters per second. So in second 2, I'm going 10 meters per second. In second 3, I'm going 15 meters per second. I am uniformly accelerating at a rate of 5 meters per second, or if you prefer to say it, and it's more commonly said as 5 meters per second squared. Let's, just for fun, if you find this fun, have a look at some other time derivatives of displacement. So I've got position here, I've got my displacement, I've got my first time derivative of that. Yeah, so if I take displacement and divide it by time, I'm given velocity. If I go for the next time derivative, I get myself to acceleration. But there's more and more time derivatives after this, which you're probably not going to be dealing with in the mechanics or studying at the moment, but it's interesting, and maybe you want to look, and maybe you want to look at some of the applications of these things. If I want to think about how much my acceleration is changing per second, the third time derivative, that is jerk. If I want to look at how much my jerk is changing per second, I refer to that as snap. And this is where it gets a little bit Rice Krispies. If I want to look at how much my snap is changing per second, we call that crackle. And if I want to look at how much my crackle is changing per second and get up to the seventh time derivative, I would call that pop. Just a little thing I've added in there just to kind of keep you intrigued that this physics stuff it keeps going, right? It keeps going. So, to summarize, speed is how fast something is moving. Velocity includes both speed and direction. That's a vector quantity. And acceleration describes changes in velocity over time. These concepts are fundamental to understanding the motion of objects in the world around us and are a key component of physics. So there you have it. I hope this introduction or this refresh or however this served you to speed and velocity acceleration has been helpful. Stay curious, keep exploring, and hopefully I'll see you in the next lesson. If you haven't subscribed, I'd really appreciate it. If there's any sort of things you'd like us to cover or any questions, drop a comment below. I'll get back to you. And if you hop into the description, I've got links to loads of my other socials on other platforms and places where you can download resources or questions and things like that. So hopefully see you again soon. Bye.